A time in 17th century France, the beginning of the French Revolution, the development of Enlightenment ideas, mathematical concepts. And there was one man, a man who lay at society's lowest point, the darkest corner, in the depths of despair. And in order to get out, he had to calculate the probability of his survival. Ultimately, he created his own mathematical concept to weigh his options of survival and escape.
Triangles are shapes that most of us probably just give a blind eye to, but you may not realize that triangles are actually a very big part of your everyday life and the things that you use. One triangle in particular that contains more rules and crazy uses than you can count on your fingers.
It is the one thing that tied this man, this tool, this occupation, this system, rainbows, galleries, figurines, light shows, Christmas trees, as well as this ugly sweater, the country of France, and the great Eiffel Tower. This triangle is called Pascal's triangle, named after this man, Blaise Pascal, a mathematician in the 17th century. Although it is named after him, he was not the first one to discover the triangle. It may be hard to believe that a triangle can be used for so many things, but we will take a look at all the patterns and their uses here.
To make up the triangle, there are a series of numbers starting from 1 at the top and infinitely increasing as you move down towards the center of the triangle, always making a triangular shape. The first row is titled row 0, the row number increasing going down the triangle. These infinite triangles can get extremely large, such as this one to the right that goes up to 92,378. The first and main pattern in the Pascal triangle is the top to bottom addition pattern. To figure out subsequent numbers and rows, you simply add the two numbers that are above the number slot below. Triangular numbers are the number of dots to make up a triangle. The outside of the triangle is made up of ones, shown here in red, while the numbers in blue are counting numbers, like 1, 2, 3, 4, and the green numbers are triangular numbers. The sums of the individual rows make a pattern that increases by a scale factor of ×2.
Another odd pattern that can be found in Pascal's triangle is the rule of exponents of 11, meaning the product of 11 to the x power, x being the row number and the product equaling the number that the row reads from left to right. For example, the third example is 11 squared, which is 121, and reading from left to right, it goes 1, 2, 1, 121.
A general observation of the Pascal's triangle is that the numbers are symmetrically organized, shown in these examples of 1, 5, and 55.
Some other interesting patterns that are present in the Pascal's triangle include the squares pattern, the Fibonacci sequence, and the odds and even pattern that form the Sierpinski triangle, a triangle that consists of infinite triangles within. These Pascal's triangle patterns can be used for many different branches of mathematics, including probability, trigonometry, calculus, solid and plane geometry, and binomial expansion.
We have looked at the different patterns found in the Pascal's triangle, but the actual defining characteristic or defining definition in its most simplified form would be a triangle of numbers where each number is the two numbers above it added together, except for the edges, which are all 1.
Right here, we will dive into the scenario that you have 6 debate team members, represented with the variable n, and 2 team members are needed, represented by the variable r. You want to figure out how many possible different pairs of 2 exist. By using the Pascal's triangle, you can take the total amount of members,
6, and use that for your row number. For the amount of members you need, 2, you can count inward on the row. but never count the one outer shell. So in this scenario, there are 15 different ways to organize the debate pairs of two members.
The Pascal's triangle can be found in everyday occupations, such as engineering, data management, airplanes, mapping, computing, architecture, and design.
So as a reflection of this project, we did this project because many people don't see triangles as complex shapes that are a tool and have a presence in our everyday lives. The Pascal's triangle proving this idea wrong, as well as a triangle interesting us because of its many patterns and trends that are simple and easy to apply to many different subjects. We were also interested in doing the Pascal's triangle because it can be found in our everyday lives. And finally, we think this project enhanced our understanding in that we have a better understanding of the correlation between patterns and shapes, as well as how they simplify more complex problems.
Just a city